Good morning to our lecturer, Dr. Shahadan, and classmate. Today, our group will present our thermal flow assignment on external flow. It's focusing on the aerodynamic of the Shinkansen E5 series bullet train. In fluid mechanics, external flow involves air flowing over the outer surface of an object at a high speed. The Shinkansen E5, or as we know Hayabusa, it operates at a maximum commercial speed of 320 km per hour, which is 88.89 meter per second. A full train set is 253 meter long, featuring a prominent 50-meter long nose profile. At this ultra-high speed, understanding external flow is critical to ensuring a vehicle efficiency and stability. Moving into the core mechanism, the working fluid here is ambient air at a standard atmospheric condition. As the train cuts through the air, it experiences two primary aerodynamic forces. First is drag force, which is resist forward motion, and the second is a lift force, which affect a vertical stability. Both forces are calculated using the standard drag and lift equation shown on the slide. This force directly interact with Bernoulli principle, where velocity change around the train body create a pressure difference, as well as a Newton's third law of motion regarding action and reaction force.
So, hi guys, I'm Dinagaran. So, I'm going to talk about the dimensionless numbers of the Shinkansen E5 series bullet train. So, we can see that Renault numbers equals to rho VL over U equals to, that is 1.184 multiplied by 320 over 3.6 multiplied by 3.35 over 1.849 multiplied by 10 power of negative 5, that's equals to 1.71 multiplied by 10 power of 6. So at this magnitude, Reynolds numbers bigger than 4000 confirming fully turbulent flow over the train surface. Turbulent boundary layers increase skin fracture drag but also delay the flow separation. So also affecting the aerodynamic stability of the Shinkansen E5 at high speeds. So Mach number MA equals to V over C, that is 220 over 3.6 over 346 equals to 0.25. Since MA smaller than 0.5, the airflow around the Shinkansen E5 classify as incompressible flow. Compressibility affects the negligible in open air. However, inside the tunnel's confinement amplified pressure wave, making aerodynamic design critical for passenger comfort and structural safety. So we move on to the next part. That is problem statement. So here got two problems, that is flow separation and air del wake and wake region and drag increase. So let's talk about the first one. So flow separation and air tail wake. As the Shinkansen E5 travels at high speed, the airflow over the curved roof and the rash section struggle to remain attached to the surface, and the boundary layer goes along the train body and adverse the pressure gradients near the tail cause the flow to detach, and this phenomenon known as flow separation. And also the The other one is about wake region and drag region. So this about behind the rear of the train and separated flow form and flow forms a large turbulent wake region. This low pressure zone creates a significant pressure drag force acting opposite to the direction of motion. The wider and more turbulent to wake, the greater the aerodynamic drag increase aerodynamic drag, increasing energy consumption and reducing operational efficiency at speed exceeding 300 km per hour.
Next, I will explain the suggest improvement to adjust the aerodynamic perform of the train. Point 1. Nose shape. First is the nose shape optimize. The train nose is elegant and constructed to reduce air resistance. This helps the train move faster while using less energy. Point number 2. Surface design. Second, we improve the surface design by removing any protruding part and making the connection between carriages smoother. This reduce turbulence and allow airflow to smoothly along the train. Point number 3, underbody and bogie. Third, we add aerodynamic cover to the wheel and the bottom of part of the train. This help reduce the disturbed airflow underneath the train, which can significantly lower drag. Point number 4. Next, noise reduction. Next, we refine the pantograph and rooftop component. This is important to reduce aerodynamic noise, especially when the train is moving at high speed. Point number 5, liquid material. In addition, using liquid materials such as advanced aluminium and composite can reduce the overall weight of the train. This leads to lower energy consumption and better efficiency. Point number 6, simulation. Finally, we use simulation fluid dynamic or CFD simulation to analyze airflow at different speed. This helps engineer identify the best design for maximum performance. In conclusion, the improvement main focus on optimize the nose design, improving airflow underneath the train and reduce noise. By implementing this strategy, the train can achieve higher speed, better efficient, and improve overall performance. That's all. Thank you.
Hi, my name is Bradley Tan Zi Liang. As we conclude our presentation of the external flow analysis of the Shinkansen E5 series bullet train, we can see how fluid machine play a vital role in the design and performance of high-speed rail system. Our analysis show that the Ronus number confirm the airflow around the Shinkansen E5 is fully turbulent, while the mass number indicate that the train operates within the subsonic and incompressible flow regime. This finding validate the aerodynamic assumption used in our external flow analysis and provide a better understanding of train behavior at high speed. In addition, the Shinkansen E5 demonstrate how advanced aerodynamic design can improve both performance and sustainability. Further such as 15-meter elongated nose and vortex generator to effectively reduce aerodynamic drags, minimize tunnel boom pressure, enhance stability, and improve energy efficiency. This innovation contribute to a smoother, quieter, and more environmentally friendly transportation system. Lastly, we would like to acknowledge the reference to support this presentation, including the works of Sanger and Kimbala, John D. Anderson, the East Japan Railway Company Technology Specification, and the CFD simulation resources used throughout our analysis. Thank you for your time and attention. This concludes our presentation on the external flow analysis of Shinkansen E5 series bullet train. Thank you.